Welcome back. Again, I'm Keith Coffey, Senior Applications Engineer for Isolation Products at Silicon Labs. Today's video is going to provide a quick overview of isolation standards and the qualification procedures for isolation components, such as digital isolators, and in systems like servers and power supplies. We'll start by introducing the viewer to basic isolation terminology and proceed from there. So, who regulates safety? Safety is regulated by a set of international safety standards whose test methods and guidelines ensure the protection of users of end equipment from electrical shock, mechanical hazards, fire, or electromagnetic interference. There are component standards such as the IEC 60747-5-2 that covers guidelines for isolation components, and system standards such as the IEC 60950 that regulates isolation in IT equipment. Technical committees maintain these standards, typically meeting once or twice per year to discuss each standard. Certification bodies such as Underwriters Laboratories in the U.S., the Canadian Standards Association in Canada, and VDE in Germany, just to name a few, provide testing to ensure isolation components and end systems meet the stringent safety standards called out in the specifications. Each standards qualification body usually has their own component standard, as shown here. So, what constitutes a safe or dangerous voltage? In plain words, what voltages can one touch and not be harmed? Well, a safe voltage, also referred to as safety extra low voltage, or SELV for short, is any AC voltage less than 30 volts or any DC voltage less than 60 volts. In contrast, a hazardous voltage is any voltage larger than 30 volts AC or 60 volts DC. Experiments have been performed and show that these levels are the initial thresholds at which damage to human skin can occur. Now keep in mind these numbers can vary slightly for a given end system specification. However, they are good rules of thumb to abide by. Regardless, any system that has the potential to expose an end user to a hazardous voltage, it must be completely encapsulated, or it must use galvanic isolation in the high voltage path to ensure that the end user is not harmed. The type of isolation required for a given end system depends on the requirements dictated by the system standard. The three most common types of insulation detailed in the standards are functional, basic, and reinforced insulation. Functional insulation is simply the insulation found in a circuit. For example, circuits separated by bare wires on a PC board. That's functional. You have to have it in order for the system or the board to work. Now, basic insulation provides one level of protection against electric shock, and reinforced provides two levels of protection against electric shock. For all end system specifications, there are two primary differences between basic and reinforced insulation. The first requirement is the 1-minute rated voltage rating across the barrier that the isolation component must meet for a system's given working voltage. Now keep in mind, the system's working voltage is the largest voltage in the system. A couple of general rules of thumb to also keep in mind is that a basic rated component usually provides 2500 volts AC rating, and a reinforced component usually provides 5000 volts AC rating. Additionally, note that every certified isolation component must be production tested for 1 second at 20% above its 1-minute rating. Therefore, a 2500 volt rated device has to be production tested at 3000 volts for 1 second, and a 5000 volt rated device has to be production tested to 6000 volts for 1 second. The second requirement is the distance requirements, or the creepage and clearance from side 1 to side 2, the non-isolated to the isolated side. A basic isolated system usually requires 3.2 millimeters, and a reinforced system usually requires 6.4 millimeters of creepage. A good rule of thumb when going from basic to reinforced is to just double all the numbers, whether it's a distance or a voltage requirement. Just keep that rule of thumb in mind. Now let's define creepage and clearance. Creepage is the distance along an insulating component's surface that an arc may travel, whereas clearance is the shortest path through air that an arc may travel. A good rule of thumb to keep in mind when safety distances are concerned is that a voltage breaks down our arcs in air at 1 kV per millimeter. So a 4 millimeter creepage component can provide at most 4 kV of isolation, and an 8 millimeter package can provide at most 8 kV of rating. However, as most designers know, isolation components usually break down through their primary internal path well before arcing across the package in air. Well, we've come to the end of today's video, and I'd like to thank you for joining me. To summarize today's presentation, note that isolation is regulated by standards maintained by technical committees. Each standard has its own set of unique electrical and mechanical safety requirements that each component or system must meet. Most systems that have safety isolation requirements use these certified isolation components to speed up the certification process, and in many cases save or eliminate 2 or 3 months of qualification. Well, there you have it. Please join me in my next video where I'll show the designer how to select an isolation component. To learn more about isolation and isolation products offered by Silicon Labs, log on to www.silabs.com/isolation and have a closer look at these robust, high-performance digital isolators and IsoDriver families. Thanks again for watching.